Hello everyone. My name is Khabar. With me, I have my partner Franz Vale, and today we're presenting our project, Almost Descending Sorting Algorithms.
This project is based on the paper generating almost descending sequences to reduce the number of movements in sorting by Yuing Yu and Zhang Zhao, published in IEEE Access. We aim to reduce unnecessary movements in sorting without losing logical ordering.
Moving on to the background, traditional sorting algorithms form unnecessary swaps even when elements are nearly equal. This inefficiency becomes significant in noisy datasets such as sensor readings, human perceived rankings, and approximate computations. The paper proposes a threshold based approach to reduce movement, slightly trading off exact ordering but greatly improving the performance.
So, our problem is how can we sort data efficiently when exact ordering isn't crucial for small differences? Our goal is to minimize the number of movements or swaps while still producing a reasonably ordered sequence. We introduce a threshold C that if the difference between two elements is smaller than C, we treat them as equal.
So if you talk about related algorithms, traditional sorting algorithms like bubble sort, selection sort, and quick sort enforces strict total ordering, even when differences are negligible. This leads to inefficiency when small variations are insignificant. In contrast, our almost descending sorting approach allows tolerance via threshold C, skipping insignificant swaps and improving performance without major loss of quality.
So the core idea is to create an almost descending sequence where only differences greater than the threshold C are considered meaningful. If the absolute difference between the elements is less than C, no swap occurs. This simple adjustment avoids unnecessary movements and improves sorting efficiency, particularly in noisy data.
So the algorithms that we've implemented are the modified versions of bubble sort, selection sort, quick sort. Their actual versions are also there for the sake of comparison. Each algorithm was adjusted to use the threshold parameter C, skipping unnecessary comparisons and reducing movements wherever it is possible.
So our project was implemented in Python. The input is a list of numeric values along with threshold C, and the output is an almost descending sorted array. We tested our algorithms on the height weight dataset, which includes real world noisy data. In each algorithm, we introduce a conditional check to treat closed elements as equal.
So for our testing methods, we compared the performance of our almost descending algorithms against Python's built-in sort function. Our evaluation metrics included number of movements or swaps, execution time in microseconds, and accuracy using Kendall's tau coefficient. Tau measures the similarity between our output and the correctly solved array, with the value close to 1 indicating high accuracy. So now we will move to the live demo, which will happen on the Visual Studio Code.
Okay, so this is our demo for the project based on the research paper generating almost descending sequences to reduce the number of movements in sorting. Our aim is to reduce unnecessary swaps during sorting by introducing a threshold parameter C where elements that are close enough are treated as equal, leading to a more efficient sorting without loss of accuracy. Now, Khabar will explain you the different algorithms.
So here we have three files. We have almost descending bubble sort, almost descending quick sort, almost descending selection sort. In all three files, we have two functions. They're almost descending function and the traditional function. Both functions are almost same except for both functions I think are equal except for one condition, that as you can see on line 9 over here, that we are checking for our C coefficient. Now how do we check it in bubble sort specifically? Since in bubble sort you compare two immediate elements or two consecutive elements, you minus them and you take out their absolute value. If the absolute value is greater than C, then the algorithm will consider them as different and not same. But if it is less than the C value, then the threshold we've set, then the algorithm would consider it as equal and will not perform the swap. Similarly, if you move on to the quick sort, here in line 16 we can see that if our value if we subtract our value and our pivot and it's greater than C, it will be considered as as not equal, else we will move on and we will not proceed with the swap. Go to the selection sort. In line 8 we can see that if the difference of the selected value and the maximum value, if their difference is not greater than C, again the algorithm would consider them invalid. the structure of all three files is almost the same except the fact that their C condition is according to how the swap is performed.
To test our function, we are using a dataset. The dataset is divided into 5 different parts to take readings at different levels. So for each length, we time the function, how much time the function is taking, and then we are storing it in a list. Then we are also using tau coefficient to compare our sorted list with the Python's built-in sorted list to check how accurate our sorted function is. These are all then returned into list, and we then plot it in different graphs to visually see the differences. We will later discuss our findings in the presentation. Thank you. So in almost descending bubble sort, we observed significantly fewer steps compared to traditional bubble sort. Runtime was also much lower, and the tau coefficient remained close to 1, indicating that even with fewer swaps, sorting quality was maintained. Bubble sorts benefit most from the threshold-based optimization. So for bubble sort accuracy results, what we have done is we have used two C values to compare how our results are affected by the different C values. As you see, a lower C value provides a higher accuracy. In this case, we are getting an accuracy of almost 98%, and for the higher C values, we are getting a lower accuracy, which is close to 90% or 89%. And if we keep the C value same and see which one is better, we see that the bubble sort gives 100% accuracy, which means that the bubble sort is giving exactly same sequence like the Python's built-in function. And for our almost descending bubble sort, we see that we are getting an accuracy of 98%. So there is a 2% difference, which is almost negligible.
So when we talk about selection sort, in selection sort, although we can see that the number of swaps remained almost the same, runtime improved significantly. This is because many unnecessary comparisons were skipped due to threshold condition. The tau coefficient was close to 1, again showing that sorting stability was preserved despite faster execution. Moving on to the selection sort results, as Irfan explained, as we explained in the previous bubble sort results, we can see that using the tau coefficient, almost descending selection sort gets a 98% accuracy. And when we check with different C values, we can see that the higher the C value is, the lower the accuracy gets, and the reason for that is the higher your C value, and the reason for that is the higher the C value gets, you start to ignore large differences, which then is not negligible. It then creates a big difference on the order.
Almost descending quicksort showed reduced time across all lengths except one, and a significant decrease in number of swaps. The tau coefficient against remained close to 1, confirming that logical ordering was preserved. Quicksort benefits from skipping minor comparisons during partitioning. We have a similar case for the accuracy results like we have explained in bubble sort and selection sort. Here we are seeing that algorithm for the C value of 0.1 is giving a 98% accuracy, and higher C values give lower accuracy. And similarly for the same C values, if we compare it with the traditional quicksort, the quicksort is 100% accurate and almost descending is 98% accurate.
So when we talk the complexity analysis, as we can see that the theoretical time complexities of the algorithms remain unchanged. Bubble sort and selection sort are O of n square, while quicksort is O n log n on average. However, the practical runtime has improved significantly because many comparisons and swaps were skipped. Space complexity also remains the same as the traditional versions. And the reason I believe they remain the same was because we just had one condition, the modified condition. So that didn't bring too much difference to the time complexity itself.
So for the future direction, one limitation of almost descending sorting is choice of threshold C. If C is too large, meaningful ordering may be lost. In the future, adaptive threshold tuning based on data distribution could optimize C automatically. The threshold-based approach could also be extended to more complex algorithms like merge sort, heap sort, and top case selection problems.